Ladies and gentlemen, good afternoon. I hope you enjoyed your lunch and you won't fall asleep in these boring SDN virtual networking presentations. Our first presenter will be Eduardo Jacob. Got his BSc and MSc at University of Basque Country. He spent several years in public research and development and telecommunication enterprises. He obtained his PhD at University of Bilbao, where he is currently leading the Information and Telecommunication Research Lab. His interests are related to application of software-defined networks to support advanced application resiliency and security, IT systems, privacy and security in sensor-based systems. He's participating in several FP7 projects. And his talk, Eduardo will present their investigation of adapting SDN in multi-domain environment. Eduardo, the floor is yours.
Thank you very much. Good evening to everybody. I am presenting a work that is the result of several persons and institutions that are all there. You see, there are several institutions. I have been working in the GN3+ project, in the joint research activity number 2, in the task 1, which is related to software-defined applications. Well, this is the agenda of the presentation. We will first have an introduction about the problem, why we think and why we have been working on this issue in the project. How is our perception of how this could be included in the bandwidth on demand service? We will present two solutions that are complementary. In fact, they build one over the other. And we will finish with a summary. Well, nowadays, I think this is almost impossible not to say that everybody's taken a look at software-defined networking. Today, even if it is not very politically correct, nowadays we can really say that at this time perhaps SDN is almost directly related to OpenFlow. So even if I say normally OpenFlow, perhaps most of the things can be also included under other approaches as PCIe. But for the sake of this presentation, when we are speaking about SDN, we will be speaking about OpenFlow. Well, nowadays, most of the important biggest 10 RAIDs are already working with that, and we have also experiences in several telcos and ISP providers which are already doing several experiments in several areas. Well, which is the objective of, which is the need for a software-defined network multi-domain approach? Well, if we want to take into account that most of the experiments are really interesting, if we merge the efforts of several people, of several institutions, at a certain point, if we want to rely on the underlying network, we are faced to the problem of how we link both domains. The objective is to support the use of aggregated resources, not only for users, but also for research. And this is interesting because normally users need services and research normally demand infrastructures or specific setups. We will say that that's why we finish taking a look at two different approaches. This is the, well, it's not very clearly seen, but, oops, I have a problem with this. The smaller one. This is the scheme of the TN+, and this is the scheme, and this is the partners who are actually involved in this architecture. Well, why we say the multi-domain SDN is interesting? If we take a look, oh my God, if we take a look at how we can manage the things, we think that there are two OpenFlow domains in which there are users that, for example, want to use resources for another domain. We could think in at least two approaches. One of them would be the end-to-end connectivity, in which we are able to set up a connection, an OpenFlow connection, an OpenFlow flow from the user to the host which hosts the services. But we have also the alternative approach, which is a federated testbed, in which we want to have a view of several resources that are inside one domain, merge them to have two others that are in another domain, and have a federated view of that platform for experimentation. Okay. In fact, this second approach will make use of the first approach, because at the end of the day, most of the things that are implemented for this original case will be the base for the second one. Well, which are the actual limitations perhaps of the bandwidth on demand service? Well, there are perhaps some limitations which are regarded that most of the services are only set up within a domain. It's not so easy to give that possibility when crossing domains. Nowadays, there are not many campuses which have also OpenFlow developed, deployed. So normally in the campus, you don't have the possibility to really deploy that service on demand. And there is also one problem in the sense that normally different institutions use different implementations to give the same service. So sometimes, even if we are speaking of almost the same things, normally there is not a one-to-one mapping of the definition of what service into the others. Well, that's why we finally arrived to the need of multi-domain technologies. Before thinking about the multi-domain problems, we must take into account several things. Normally, if we want to put in collaboration several domains, at least I am a researcher, I don't work for any IT services in any university. The view we have is normally the university won't share details of its internal resources to anybody else. So if we are used to thinking experimentation, thinking I know every switch in the platform, I know where every port is connected, I know the DPIDs of everything which is in the network, it's something that it's very, normal to think in this sense. If you are thinking with NRENs, with institutions, with providers, they normally don't want to share details. First, because of security issues, because it's giving too much information that you will never know when it will arrive. And normally, they don't want also you to tell them which are the resources you need. I mean, normally, they accept the fact that have a connectivity from the connection point to a host, but they don't want you to tell you which is the path to take or which is the alternative to take. Well, that's because sometimes if they take into account your solicitations, normally they will finish deploying non-optimal solutions. So normally, this is normally something that they don't want to do. Well, if we use some OpenFlow rule to define the services, we get a granularity which is perhaps better than the granularity we can get with other approaches. And this granularity is perhaps fine because it's interesting to get rid of templates. I mean, we can live in a world without templates. If I can define a service on demand based on an OpenFlow flow rule, I don't need to have a repository of services templates. Another thing is that I don't need to expose the full range of services and on one connection all the possibilities. Well, in fact, there is another thing to think about. If we use an OpenFlow enabled domain, we can have some optimization techniques in the traffic engineering, which could be beneficial for the infrastructure, which is in fact one of the OpenCall projects of GN3+. Well, the general case, if we think, could be the use case of the bandwidth on demand, in which we have a campus network, which, for example, is OpenFlow enabled. We have another NREN, for example, which is non-OpenFlow enabled or it is, and we arrive to another service in which there are some resources we can access. So the use case means to deploy bandwidth on demand services that expands not only the core but also the campus domain. Well, a general scheme would be something like this. This is very clear, very typical. We have first an initial phase in which both network providers get an agreement on the type of services they can accept. I mean, what does this mean? This means that if, for example, one provider is able to supply you any flow you define in an open flow rule, but another one is only able to supply you VLANs, this means that you must know what you are able to supply to the other one. So one, this is an old version. This is not the version I was intended to put, because at a certain point this was not correctly put. This should be there. In fact, what happens is that a user wants to connect to another resource. The network provider must be sure the other network provider can supply that connection. Well, I will update this on the presentation because this is not the last one I intended to put. Well, we can take another look at it. The case one, if we are thinking in SDN open flow domain and a non-SDN or non-open flow domain, we have to tag the services in a way. The normal way to do this is to tag it with VLANs. This means that at a certain point, for example, it's quite easy to tag domain here. We arrive here, and if this other domain supports also the VLAN, there is no problem. It's a one-to-one mapping. This means that, for example, if the definition of the services is coherent, I mean, for example, in the open flow domain, you can really define a service by a MAC or a MAC range and a VLAN. If you are able to make this through the second domain just using the VLAN, this can work. If the definition of the service is not so easy, the services that are defined on one side are the services that can accept the other side are not coherent, you have two possibilities. Either reject directly the connection request or hack a solution. Hack a solution, or what could be done? It could be, for example, just tunnel it in a certain way using MPLS, using QinQ, whatever. In some sense, this has the objective of not changing anything of the service the user is sending or is asking you. The other solution involves rewriting parts of the information the user sends. This means that, for example, you could, for example, if you arrive here and you just are able to supply VLANs and one guy is using inside that flow the VLAN you're already using, you should be rewriting VLANs. If you want to use a special MAC address which is not able to be transmitted over your layer 2, you could rewrite it. But normally this means that you have to maintain a state at supply information between the two ends in your domain. So perhaps it's not so scalable. Well, if you use two SDN domains, this is, at least in principle, easier because you don't have to tag explicitly any service. You just define it, you just send it, and you just define the flow rule that identifies it. And well, there are other issues. For example, the protocol. I mean, this is not if you are not using the same protocol, this could be a problem because the flow rules could be different. And the good thing is that, as I told you, there is no need to explicitly tag the traffic, and the traffic doesn't need to be modified, which is quite interesting. Well, the extension of bandwidth on demand, for example, services to an SDN-based campus network should support these classical requirements. You should, I mean, they are quite common, so perhaps I will not go through them. It's something which is quite standard. And if we take into account which would be the last requirement, we would like it to be able to be service agnostic. I mean, it should be valid, the multi-domain solution should be valid for any combination of open flow and non-open flow domains along the path. We have presented just a the smallest, the simplest case possible, but it should be interesting. This means that at a certain point, we should guarantee that the service is going to be provided every domain, even there are domains which does not support that level of granularity. That's why in the work of the project we have taken two approaches. One is the connection-oriented, and the other one is the slice-oriented. The connection-oriented is a transversal solution which is used as the basis of the slice-oriented, as we will show now. Well, we found that the Network Services Framework, NSF, is the ideal candidate to provide this capability, and the framework provides some network services interface, the connection service, the topology service, and the discovery service. Why we choose this one? Because on the first hand, NSF is technology agnostic. It was designed to work regardless of the underlying technology, and in fact we have been shown this morning the use with lambdas and this kind of stuff. So initially it's a good idea. And another good thing is that the NSICS, the connection service protocol, is easily extended. NSF takes into account two different topologies. One is the inter-domain topology, which takes into account how different domains are linked between them, and the intra-domain, in which takes into account the resources which are within the network. This is where the network resource manager appear. Well, if we take a look at this, what we have finally is we have first network service agent will be the first one will be the ultimate requester agent, which is in fact the agent that starts the connection request. You will have the ultimate provider agent, which is the entity that finally offers the service. They will use the message transfer layer to interconnect these entities, and they will exchange NSI protocol. The NSI protocol, when arrives to the provider, in this case, if the provider domain is an open flow, an SDN based, the network resource manager, in fact, will be an SDN open flow controller. What does this mean? This means that the coordinator at a certain point, taking into account all the configuration he's already running, he will be able to configure the rules and the services needed in order to provide the service. One interesting thing is that the NRM is out of the scope of NSI. That's not part of the standard, so you can do whatever you want. Well, there are some challenges if you want to integrate OpenFlow in NSF. One of them is the granularity that OpenFlow provides is much bigger than the granularity you have with the original NSI. Because OpenFlow, as you know, can define a flow in every combination of L1, L4 information. This means that we must devise a way to passing the information. How we do this? We do it extending the NSI connection service. Here we have two possibilities which are under study right now, and even we have in the scope the next version, which is version 3.0. We have also an adaptation capacity. Well, NSI version 2 will support the extension of the protocol functionality without touching any other parts of the protocol by two different means. One of them is extending the meaning of any attribute of the messages changing the namespace instead of using the predefined one, or coding by coding the L1, L4 into the STPs. We have two possibilities. Define a new service, extending the existing point-to-point service to support these 4 layers, this 4 layers based definition of the flow, or defining a specific open flow aware namespace and use it in any attribute of the reserved messages. Well, if we arrive now, after having taken a look at the slice-oriented solution, we now see that the slice-oriented solution have another objective. In the first case, we were speaking about setting a flow that goes from one user to another user in different domains. Here, we are speaking about creating sets of isolated resources that should be connected through a federation scheme. Well, this means that finally we will be able to create slices around the multiple domains, and we will have the end-to-end connectivity needed for deploy this done with the previous explanation. Well, there are 3 server services involved: the connection management service, the slicing management service, and the compute management service. There will be an orchestrator which will act as the management platform. We will coordinate the services and delegate the execution of operations to each of the domains, and it will be based on the slice-based federation architecture which was already used in Planet Lab, for example. Well, this could be the view of a slice-oriented multi-domain connection. We have one software-defined working domain. We have, for example, GN. We have another software-defined domain which would correspond to different endpoints. And we would have several SDN domains controller. And what we would finish is having a slice that would use several resources of different domains. Well, everything is done in base of service termination points. Well, the solution here has in the scope using a tool which is named OpenNAS, and this will implement the orchestrator of the solution. This orchestrator has at least several modules, which are the aggregator, the OpenFlow Resource Manager, and the Aggregate Manager, and it will constitute the orchestrator of such a solution. So finally, these are the summary and the future steps. We have presented why multi-domain SDN OpenFlow is interesting, why we choose to separate in two different ways. At a certain point we had some discussions that took some time because we were not so confident on having two different approaches, but finally we saw that one could make the use of the other, so that finally was not a so bad idea. We are already beginning the coding of the connection-oriented solution, which will be a traversal solution that will be used later. And well, in this first solution, as we told, the network resource manager in the OpenFlow domain will be an OpenFlow controller, normally probably Open Daylight. Finally, the slice-oriented solution will use the services of the first scheme. I will be based on OpenNAS as the orchestrators. Well, and this is all. If you have any questions, I will be glad to try to answer.
Thank you very much for your presentation. Any question from the audience?
Can you talk about how your approach is similar to or different from the Genie approach?
From?
Genie. G-E-N-I.
Yes, Genie. To tell you the truth, I am not the best for answering you, because I told you I have been here presenting this by accident. So, in a certain way, I'm sorry, but if you give me some resources, I think I can answer you. I will bring you the answer. Sorry about this.
I would have a similar question, but not the Genie one, but what about the other giant service under development, the SA2 testbed as a service, how it would relate to that research and development?
Well, I can answer, but I can answer from the view I get from working on another project, which was initially working on the giant OpenFlow facility and is being migrated of the new infrastructure. So that's the view I can say. I think that in SA2 you have the possibility to get a view which is much more linked to the view you need to your project. So it's perhaps not so fixed. I mean, here if we think about how an NREN, and I speak about the NREN, I know a little, which is the Spanish one, and I speak about the campus network, which is one university, which is not a very big one, but has 3 big campuses. I mean, and I know that this kind of architecture is more easily adapted to that solution than perhaps SA2 service. So if you speak in the sense of the core network, I think it will be not a problem, because normally it will be very compatible to that.
Okay, thank you very much. Any other question? Yes. Over there.
Hi, Joan from I2CAT speaking. Very brief question. You mentioned you already started implementing the connection-oriented solution. Did you contribute the specs to the NSI to get feedback before starting the implementation, or you plan to do it later on? Thank you.
No. Well, in fact, there are also other people from I2CAT involved in the effort. And at this point, we are, in fact, the last working document we have is the functionality definition we expect for the first implementation. So we are now defining which are the requests you can do, which are the answers you will get on regards to the NSI dialogue. So we are beginning to that, but there is at this moment still no coding.
If there is no more question, then thank you very much again. And our next presenter will be Alexander Gall, who is a network engineer at Swiss Research and Education Network. He specialized in design and operation of IP-based backbone. His area of interest is including routing, IPv6 and multicast. He also part of performance enhancement and response team at Switch. He holds a PhD from Bern University. Alexander will speak a completely different aspect of SDN usage, using SDN to create VPNs in an MPLS-free network. Alexander, please give your presentation.
Thank you, Janos. Right, from the somewhat convoluted title, you see that I'm fully buzzword compliant for this session. So there's SDN in it, there's something as a service, and there's MPLS. But as Janos mentioned, my approach is somewhat different to what people usually do with these things. And I hope that the aspects that I'm going to highlight are maybe a little bit new to some of you, and in any case interesting. So this is a short overview of what I'm going to cover. I will start just briefly describing our design of the backbone, how we run and operate the backbone, because that will be a motivation to the actual project that I'm going to talk about. So this is about one application that we have, which is a Layer-2 VPN, and I will briefly say how we do this today and how we would like to do it tomorrow. And that will bring me then to the actual, the centerpiece of the presentation, where we are limited actually by something I call a vertical integration of current network devices that I intend to overcome with a kind of one of the possible definitions of software-defined networking. And then at the very end, so I'm actually building a box, and in lack of a better name, I call it the SDN VPN box, and I guess I should find a sexier name for that at some point. So this is our network. This is the layer 1 infrastructure. So we have our own dark fibers, and the reason I show you this picture is because of the next one. So I briefly flash back and forth. This is the layer 3 topology, and if I go back and forth, you can somehow see that these topologies are, almost practically the same. That's one aspect of the design of our network, that all of our POPs are actually host a router. So you can immediately see that we love routing. We really like that. We do routing everywhere. Another aspect is that customers are directly connected to these POPs directly. So there are no more boxes than are on this picture, right? So those are the principal, the features of our backbone. We basically, what our job is to provide IP connectivity. We do this for IPv4, IPv6, unicast, and multicast. So we provide internet access for our customers. That's basically it. Our strong belief is that anything else, and whatever our customers do, should be implemented as some service over IP. So our backbone transports IP. That's what we do, and I think that's what we do well. Also, I just mentioned that our hierarchy is flat, so we don't have like customer edge and a provider edge and a core network. We don't have that. Basically, all of our sites are on the backbone. That has certain implications on the way we have to run things. Also, so we do IP routing. All of these links that I showed you are basically point-to-point IP links. We really, really hate extended layer 2 domains, so we try to do that as little as possible. And we rely on plain IP routing in our IGP for failover. So I can summarize that by saying that what we really love, our mantra is this: simplicity, efficiency, and robustness. That's what we want to do. And our enemy number one is complexity. So whatever we do, we try to do it in as simple a manner as possible. And in the current context, this means that specifically we don't like MPLS. Now, I know many people do like MPLS, so I should probably say a few words why we don't like it. And there's a generic part and a more specific part to that. So obviously, it's more complex. Nobody can deny that. You need additional protocols to make it work and so forth. You need different tools to troubleshoot it. Ping and traceroute is no longer enough, et cetera, et cetera. Now, I would even go as far as saying that, well, to me, there's really no reason that MPLS exists at all except for historical reasons. So I realize that many people will disagree with that. But I suggest that we take this to the coffee break. But one concrete problem we have with this, because of our flat hierarchy, MPLS is a provider feature. That's because usually networks are built in the manner I described. You have this customer side and the provider side, and the provider is doing the complex stuff, including MPLS. So that often means that certain low-end boxes don't even have it implemented. Some vendors, when it's implemented, they charge you in addition. You have to buy an additional software license to enable it, and so forth. So when we want to connect or supply a Layer 2 VPN with MPLS to one of our smaller sites, where we really want to have a cheap, small box that is located on the customer premises, then MPLS is actually hard to get there. So that's our main motivation why we don't want to do this. So as a further input to the question that or the problem that I really want to solve is, a short digression about how current network boxes are constructed. So whatever all of us here in the room that run networks, the boxes that we buy, they all rely on specialized hardware, ASICs kind of things, because that's the only way we can handle the traffic levels that we need to handle, right? So they also have generic CPUs to run the control plane, but those are usually, for a reason that I never quite understood, but they're usually also several generations behind what you would consider like high-end CPUs. So they can barely, so they can do what they need to do, run routing protocols and so forth. Some operating systems also would be able to forward traffic in software, but it's completely unusable. When with any kind of significant traffic, these boxes would fall over immediately if you run it on the CPU. So that's what I call the vertical integration, because the hardware is designed by the vendor, and the software that you need to run it is also supplied by the same vendor. That immediately has consequences that whatever you want to do, whatever feature you want to use, needs to be supported in hardware and in software, obviously. Otherwise, you cannot use it. So I would like to, as an example, discuss how this looks like in the case of simple Ethernet tunnels, layer 2 VPNs. So I call this internet as a cable. Some people like it to have one side, remote sites connected by a network that they want them to look as if they were connected by a simple Ethernet switch or an Ethernet cable for one reason or another. So actually, some of the reasons are up here. So maybe they just want to connect two sites without having to do any routing. Sometimes they just want to backhaul all the traffic to the main side where the big firewall is and then route it to the internet from there. It could also be cheaper to only buy uplink internet connectivity from one side. So those are some of the reasons why people, at least in our environment, like to do this. It's a very simple service. So basically what we give the customer an additional port on their access device where they can plug in their Ethernet cable, and they connect another device on the other side of the network at the remote side of the same customer. And all the Ethernet frames that come in on one port come out the other end. So it really looks like a long Ethernet cable. And because the network in between is not an Ethernet network, we need some kind of encapsulation to transfer these packets. Basically, there are two flavors. The most simple one, and the one that I will restrict my talk to that particular case, is a point-to-point link. That's the most simple case, just two endpoints, exactly two endpoints. Sometimes people also call this a private virtual wire. You can also have the semantics of a multi-point network, where basically you get the equivalent of a multi-port switch. So there's basically a set of point-to-point links with additional MAC learning and forwarding tricks. Not very much different or much more difficult to do. So we have to encapsulate it somehow. How can we do this? Now, one way would obviously be to just use IP to encapsulate, take these Ethernet frames and just pack them into an IP packet. And of course, there are various ways you can do that. This is nothing new. You can, it works over IPv4 and IPv6. You can then use any kind of encapsulation that you choose, GRE, L2DPv3, UDP. If you control both endpoints, you can actually do whatever you want. It's only the endpoint that really need to know how it works. That would match our design of our network perfectly. It's a service over IP, and we know how to do IP well, so everything would be fine. Also, in our case, if you do this service with MPLS, but you don't do anything else with, that requires MPLS, like traffic engineering things, fast rerouting or stuff like that, then encapsulating it in IP is exactly the same as doing it in MPLS. So the semantics of the service is exactly the same. You don't lose anything. It's 100% equivalent. In addition, in my opinion, what are really benefits are so the network in between doesn't have to know anything about it. And it would also trivially work across domain boundaries, which I think is a good thing. So that's what we want to do. I know exactly how I would like to provide the service, but I cannot. Why is that? That's because the equipment that we're using, and so there's the list of the stuff. We are Cisco shop, and those are the devices that we use. And they simply cannot do the thing that we need efficiently. So all they provide to me is this kind of service over MPLS and not over IP the way I want to do it. I think some of these combinations of chassis and supervisor are actually capable of doing some form of this thing, but not all of the variants we have. And also these are big, some of the bigger boxes. We also have, for smaller sites, we use different devices where, as I said, there's a problem to get MPLS there. But even if the hardware itself, the chip, the ASIC on this thing would support encapsulation of Ethernet over, say, IP GRE, if the software does not allow me to configure this, it's worthless. It's not available to me. So that's why I said you need support from both the hardware and the software to make this work. So the conclusion is that I know exactly how I would like to provide a service, but my vendor doesn't allow me to do it. So that's the problem. And now here comes in SDN. And you're used to, when we talk about SDN, most people these days actually immediately think about this paradigm of the separation of control plane and forwarding plane. This is not, well, this is a useful definition in many cases, but in my case, I would like to have a broader definition. And since SDN is such a new thing, I think we're all entitled to our own definition of SDN, and I just choose to use a different one. You can also have a much more general definition. Namely, you simply say SDN is a mechanism that allows me to make the box that I bought do whatever I want it to do and not what my vendor allows me to do. And that would also imply that I have full access to the hardware, to all the features that the hardware supplies. So these two definitions, you have a broad spectrum of things, how boxes could look like. So you could have traditional routers that you buy today with an added API. Some vendors actually do that, that now supply an API that allow you to actually access parts of the device that were not available to you before, which I think is actually a good thing. You can take this further and standardize this API. Then you end up with something like OpenFlow, which is, of course, also fine, very good. If the community agrees on a common API, this is much more useful. Or at the upper end of the spectrum, you can take a completely custom-built device and you can do with it whatever you want. And you can still call it SDN. So I'm here. So that's what I consider in my approach here. That's the definition of SDN that I'm using. So one interesting aspect is, why can we talk these days? Can we actually talk about this? Building a custom device and doing something with it that requires, where you want to be able to handle a fairly large amounts of traffic. So the recent advances with commodity hardware allow us to do this. So for example, modern last or generation Xeon processors have some features that weren't there before that for example, they have onboard, on-chip PCIe controllers and memory controllers. They have additional inter-socket links, very powerful. They have more cores and so forth. So please don't press me on the details. That's not my field of expertise. There are people on this conference who can tell you everything about these things. One thing, if you wonder, well, what can you expect from these things, from these kind of chips? So this is a number I got from somebody who heard it, that there is some benchmark from Intel. So I don't really know where this comes from, but I suppose the ballpark figure is correct. So a packet comes in on one port, and you do a simple forwarding lookup, and you send it out another port, and supposedly these chips should be able to handle on the order of 10 million packets per second per core, which is pretty powerful. I guess it's an upper limit of what you can actually do, and this diminishes the more fancier things you do to your packets. So the same thing goes for network cards. So you have very powerful cards out there that have tons of features. They're very well documented. They're cheap. You can buy them. You can program them. You can do anything you want to do with them. So in principle, with all these figures, if you do it right, you can build a device for very little money that has the potential to be a very powerful networking device. So that's why we can actually start talking about building things like that. Right, so the goal of my project is to use these kind of devices to solve the problem that I told you about, namely that we would like to build our Layer-2 VPN service on top of IP. And so I would like to leverage all of these properties to do that. I could have taken the cheap way, just take a Linux box. Well, I have to say that most of our customers actually order 1 gigabit point-to-point links, a few also 10 gig, but most of them 1 gig, and that's not too hard to do. I could have taken just a Linux box and probably wouldn't have needed to do any programming at all, just use them as encapsulating and decapsulating devices. But I wanted to do something more interesting and something that has the potential to be actually more useful than just that. So the approach I've taken is, I don't know if any of you heard of this. There's a guy called Luke Gorey, an Australian, who developed a framework. You can find the details here on this website. That's very interesting, a very general framework to do networking on commodity hardware in a very special way. There's a Google forum where people discuss these things, and there's the code is available on GitHub. Snap, I think, so he's Australian, but he lived in Sweden for a long time, I think. So, and Snap, as far as I know, is fast in Swedish. So this project is called the Snap Switch. So it's a fast thing. So the interesting thing is, one aspect of it is that it all runs in user space. There's no kernel space involved. And that includes the actual network driver, which is also written in user space. So that actually outperforms kernel space, and there are no detours. If you actually use the kernel, even though you don't want to use most of the features, there's still code paths that you have to go through because you just cannot turn them off. Or you don't really have control what your packets are doing in the kernel. So also it makes it much easier to develop in user space than in kernel space. If you really want to get your stuff into the mainline kernel, this takes a long time and a lot of effort to do that. And if you don't do that, then you always have to make sure that when you upgrade your system that you have to update your own kernel module and so forth. It makes it hard to manage. It's harder to debug. If it crashes, it likely takes down the whole box. It doesn't happen in user space. So the programming is much easier, and it's even more easier when you realize that the software framework that's used in this project is actually a scripting language. For those of you who know Lua, it's very much like Python and Perl and Ruby, stuff like that. So a high-level language. And it's actually true that even the device driver is written in this language, which is kind of amazing. It's possible because it comes with a very powerful just-in-time compiler that produces really fast code. So one of the mottos of this project actually is that it should make fun again to write device drivers. And it actually does, because it's very simple. The switch itself, the focus of the project is really not what I'm doing. It's more focused on the virtualization, network virtualization on hypervisors and VM and so forth. So that's also why it's called the Snap Switch and not the Snap Router or something. But I realized that I can use the same box, the same software to actually just do what I want, which has nothing to do with virtualization. So it perfectly matches what, how we like to run our network. It's very simple, and the philosophy is you just do what's the minimum you need to do to accomplish something. So you leave away everything that's not necessary. So that's very appealing to us. Also, this guy is also involved as a consultant to the TerraStream project of Deutsche Telekom, for those of you who heard of that. That's also a very interesting project, and they, the approach they're taking, I can sympathize a lot with them, because they're also taking it to quite an extreme, because their backbone is actually IPv6 only. There's no MPLS, there's no IPv4, there's just IPv6. And everything is implemented as a service at the edge of the network, including IPv4. So this sounds very similar to what we like to do. Of course, there's plenty of interesting virtualization stuff going on, but it's all at the edge of the network. So that's the difference. And I think that is a very good strategy. So the box itself, it's exceedingly simple, of course. Encapsulation, decapsulation is not a complicated matter. So it looks basically like this. So this is the physical box. It has two interfaces that are dedicated to the VPN. One is connected to the customer side, and the other is connected to the backbone side. This box is co-located. It stands right next to to the access router, the access device of the customer. And whatever packets come in here take this code path, and then you simply add an encapsulation header and send it out towards the backbone. And packets that come in are expected to be encapsulated, and then we remove the encapsulation and send it out to the customer. There's no routing going on in here, not at all. The interfaces are completely detached from the Linux kernel, so I have complete control over these devices within this software here. There's, of course, the traditional Linux kernel runs on the box, and it can have any number of other interfaces that are still managed by Linux that I use to access the box and manage the box and so forth. I chose to implement the encapsulation in IPv6 only, because our network supports IPv6. There's no reason to do it in IPv4. So I use dedicated IPv6 addresses to identify an endpoint of a VPN tunnel, and right now I just have a static route in the backbone that points to this interface. So that's basically it. Very simple. So again, yeah, that's what I'm doing. In my case, I'm using GRE for the encapsulation, which is kind of arbitrary. I could have used any other scheme. It doesn't really matter. So when the packet comes in, I just do the encapsulation, and of course the reverse operation is also very simple. So what are the experiences? So this is all very new. The entire framework is really new, and it's certainly far away from any production grade services. But I think there's a big potential, and we still have to learn a lot and find out how to use this best. So like performance is an issue, and whenever you use like a high-level language and you want to have high performance, and in particular in the networking device and the forwarding path, where you don't really want to have like random jitter and maybe even longer periods where no packets are forwarded at all, that's a bad thing. You don't want to have that. And so I could make my application work, but I think there's a lot to learn still there, how to do that properly. And because this can really bite you, in particular this garbage collection. So this is dangerous, and we have to be very careful how to avoid this. My own application, this VPN tunnel, is also, right now it's kept to a bare minimum. So I said there's no routing, there's also no real neighbor discovery. I implemented like a very simple thing, so I don't have to configure static MAC addresses in the backbone side, so that works. There's no fragmentation right now, so I have to make sure that the MTU in the back between the endpoints is large enough so that I don't need fragmentation. But that's all stuff that can be fixed. I just have to add this code. if you're interested in the performance numbers. So my code is also available. It's part of the code that's available on GitHub. So my box uses these new type Xeon processors and 2-port Intel NICs, 10 gig NICs. So my tests where I simulate this in actually a real life scenario where it crosses our backbone links and I get up to close to 6 gigabit per second, and the limit does not come from this box but from the rather old endpoints where I run iPerf on. And I don't see any artifacts, at least with iPerf, so it runs smoothly and stable throughput, so that's encouraging. Management and monitoring all of that is still a wide open question. Of course, it's a Linux box, so we can implement whatever we want, whatever we think is useful. We can implement SNMP. The plan is also to use netconf to configure the box and so forth. So they're very flexible, but nothing has been really done yet. Right, so this brings me to the end.
Thank you very much for your presentation. There is a question here.
Well, it's just a suggestion. Let's call it the Alex box. It should have a name. You know?
Yeah, actually, internally, I think some people already call it that.
Maybe I have a question. Can you say something about the scalability of your solution? And then other question, what do you think about or did you have any request from your users, a multi-point layer 2 VPNs, VPLS solution? Can you imagine how it could be implemented in your architecture?
Yes, so the scalability, you mean adding more ports yeah. So I think it should scale fairly well because you can make use of the multiple cores that you have, and you can dedicate. I have to say that the code actually it runs. It's not multi-threaded, so it's a single thread of execution, but you can schedule it on a particular core, and that should scale very well. Of course, if you then start doing forwarding between arbitrary ports, then this gets more tricky, and we have to find out how that's going to work. So I cannot really tell you anything specific how well this will really scale. But yeah, I think there's enough potential because of the way that the software works on these kind of systems. The other question was about multi-point. Yes, so we have actually we have one single customer so far who actually uses VPLS, and my plan is to actually also provide that with this thing point-to-point link as a building block, and my plan is to simply provide a full mesh between the sites and then add a little bit of code that makes sure that the Mac learning thing and preventing loops and so forth. So that's a rough plan. I think that will not scale to arbitrarily large VPLS installations, but our customer base is small. Like our current customer only has 3 locations. So for that kind of thing, I think it would be pretty simple to implement that.
Okay. Any question? Yeah, there is a question over there.
What's your security model for this? Is it left as an exercise to the end user?
Well, you mean the security of the tunnel itself? Yeah.
What do you say?
Yeah.
What kind of
security?
security?
Where does it sit in the framework of network security?
So that is, as you say, this is. I know you should take security into account from the very start, but so I think there are different aspects. Like I say, the actual security of the transport of the packet itself and the security of the box itself. I guess those are two separate things. For the transport, I suppose you can do. You don't have to invent anything new. It depends a little on the encapsulation that you use. Like if you use GRE, and then there's this key field that you can use for whatever purpose you want. In MPLS, there's also, for the transport of the packet, there is also very little in that respect. But in general, we can, I guess we have the full freedom to implement the measures that we at some point think are important.
I had more in mind the security of accessing the service in the first place.
Accessing, you mean as the customer side of it? Well, I think it very much looks like our current service where the customer, the box is located on the premise of the customer right next to his internet connection, and he just has an additional cable that plugs in, not into our router, but into the box that sits next to it.
Hi. Have you looked at hardware encapsulation capability as an alternative to implementing a data plane in software on a server? Like, it seems something that's very popular in the data center space now for interconnecting data center stuff is something like VXLAN. Have you investigated hardware that can actually do exactly what you want?
No, I did not. I think the hardware that I'm using, so these 10 gig adapters that I'm using, I think they cannot do this. But I was also interested in how far I can get performance-wise without hardware acceleration. Because then you're most flexible, then you're not required to use a particular kind of hardware that supports this and to make it work. So actually a goal was specifically to see whether I can get, with a pure software implementation, decent performance that makes me independent of that. But of course, when it's available and it's possible to use, then that would also be an alternative. Yeah.
So did I get this right that currently it's only a port-to-port service, so no VLANs, yes. No VLAN tag rewriting or something like that?
No. It's really the most simple form because all the other problems were more difficult to solve. So I just focused on the most basic thing you can think of, which is a point-to-point link without anything. But it will forward everything that comes in. So if so it's oblivious to whether you use VLAN tagging or not. It will just forward everything. So you can use it as a VLAN trunk if you want.
And do you have already slight idea how the system behaves when you add new features like SNMP or maybe VLANs or something like that?
No, not
yet. Will it still behave
right.
according to expectations?
Yeah, that's a good question. These are all good questions. So my expectation, at least my hope is that all of this should not be difficult to do, and it should be possible to make this perform well. Just to add, it would add a small amount of overhead to it, but hopefully that will, not be a killer for performance. But these are all things that we have to find out.
Yeah, last but one question from the middle, yes.
Okay, about the overhead, did you try to have other solutions? For example, not using a Linux kernel, using a microkernel style, or using other hardware that can be open, like there is an open compute project that can help you with that?
No, I have not looked into that. That's just because the framework that I've chosen doesn't do that. It's really targeted at a Linux platform actually it only supports a very small set of drivers, basically a few Intel drivers, so we're restricted to that environment right now.
Yeah. Thank you very much for your presentation. I really see the potential, especially in the future, because of the commodity Intel hardware is becoming cheaper and cheaper and more performant. So I think there can be some potential in such a development. Thank you again for your presentation. Our next speaker will be Inder Monga, who serves as a chief technologist and area lead of network engineering tools and research at Energy Science Network. He plays a key role in developing and deploying advanced networking services for collaboration and distributed big data science. His research interests include network virtualization, software-defined networking, energy efficiency, and distributed computing. Mr. Monga will investigate in his presentation how software-defined networking is influencing the BOD, bandwidth on demand, and natural evolution of bandwidth on demand to entire virtual networks on demand. So it seems to be complicated, but probably Inder will make it easier, yeah, for us. Thank you.
Thank you. Hi, everyone. So I have to give some warnings. And the warnings is in that critical look. This is not a forward-looking talk. So I'm not talking about what's going to be fun and wonderful in the future. It's actually a backward-looking talk. So just bear with me. So it's not about what in the future. So it's more what hasn't worked and what we should do about it. So really quickly, I mean, I'm going to focus on bandwidth on demand, but I'll just say that I want to excuse ESNet for all my comments here. So I'm speaking just as myself and not representing thoughts of my organization. So I just want that to be out there. So don't go and blame any of the other ESNet people on what I said. You can come and so I'm giving you a little bit introduction on bandwidth on demand so that we are on the same page. History of where bandwidth and demand has been, some technical challenges, and talk a very high level and very briefly about programmability and BOD. To really do this subject full thing, I needed a lot more time, an hour, but so I'm kind of compressing a whole bunch of stuff. So please and feel free to ask questions in the middle or after the topic. So I think this is something very simple. You know what bandwidth on demand is. You just create a connection between 2 points based on a request dynamically and allocate certain guaranteed bandwidth. One example which has been used forever is the phone, right? So you pick up the phone, you call someone, you get 64 kilobits per second guaranteed bandwidth between 2 people, and you talk. And in data world, it's called a virtual circuit, and then you connect 2 computer networks together. Very simple. But there is an R&E twist to it. The reason why the research and education networks have had a twist to it is they want it to be application driven, not human driven. They want it to be multi-domain because science is a global enterprise and you want to go multi-domain. You need bandwidth reservation and guarantees and on a calendar, so there's a start time and an end time. And then, sometimes you make errors in your start time and end time and you want to be able to modify that in the middle. So these are some things that have got complexity into a simple bandwidth of demand of setting up a circuit and then having some bandwidth between them. So just keep these in mind that these are additional requirements that we have added to the bandwidth on demand picture. So let's go through the history really quickly. So we see where bandwidth on demand for data has been. So obviously, why there are no text coming? This is interesting. Is it because it's a PC? It's a Mac and PC issue, I think. Okay. Now it's coming. Okay, fine. Okay. So the first one obviously is modems. So you could, connect your computer to a modem and get some bandwidth on demand. You just got, depending on the capability of the modem, you got 56 kilobits per second, 9600 baud. And that is since 1962, modems were invented with 300, I think, bits per second, and they evolved over the next 20 years. Then came switched virtual circuits, SVCs. I hope you remember them from 1980s. It was X25 SVCs, ISDN as a thing. You remember ATM and frame relay. I think they should be switched. Frame relay was before ATM, but now none of these, they were all, ISDN was deployed, but never became a successful service. X25 was deployed, but PVCs versus SVCs, and similar with ATM and frame relay, what was really deployed was PVCs, permanent virtual circuits, rather than switched virtual circuits. So those bandwidth on demand from that perspective wasn't that successful, in my opinion. then MPLS and MPLS-TE, which has been really successful. But then OIF, or Optical Interworking Forum, took that and create, bandwidth on demand protocols with UNI, INNI, and ENNI, and that hasn't taken off. I mean, they have done numerous demonstrations, but that hasn't taken off or adopted or deployed by the carriers. Then I know, again, same problem. Yes, there was, as at Nortel, I worked on 2 projects, content over optics and DRAC, and they were fairly successful. Not really. I mean, they were successful in the sense that we got an R&D customer, but it didn't become successful commercially in the sense that commercial carriers didn't deploy them. There's Oscars, which is deployed as production within ESNet. So I've experience with that. It runs very well. It is deployed in Internet 2. It is deployed in a few other networks. So that was something that is working. And then, from a multi-domain perspective, there was IDCP, which was a protocol created by some networks that got together, and it worked as a technology, but it wasn't successful in capturing the R&E imagination for layer 8 issues. And then OGF took on through this Grid High Performance Working Group in 2004 and has worked on interdomain protocols NSI version 1 in 2012 and NSI version 2 in 2014. So this is kind of the history of bandwidth on demand as far as I know it. And I'm sure I'm missing something. I'm missing UCLP, which was around the same time frame, I think around 2001 time frame, which Canary was doing, and a few other projects, Autobahn, around Oscar's time frame. And there was, I think, something which I didn't have time, is there was an Internet 2 Brew project, BRUW. I think Eric might remember that. Yeah, Oscars was part of that. So anyway, so there has been a lot of time we have spent on bandwidth on demand. And the question is, after a decade of bandwidth on demand demonstrations, are we there yet? I conjecture we don't have a universally adopted operational service. And why has that been challenging? Number one is not all R&E networks and not end sites are believers. I mean, you still heard in the session today that not everyone is a believer in that. It's not a seamless end-to-end operational service, which means it still requires manual intervention at the edges. You still have to configure VLANs manually, and it is dependent on the network technology. That means not all devices or not all equipment can support guaranteed bandwidth. So you have to kind of work with that. So you can't provide a consistent service. It depends on what network technologies are there. The software and protocols, as you saw the history, have been in a continual state of evolution and debate. And it is not being implemented in carrier networks yet. So there is no big commercial driver forcing commercial vendors to build this technology as a default thing. So kind of it's more us building it as research projects and then taking it into production. But everything is not black and white. I mean, you can't say it's not successful, it's not worked. So let's look under the cover, see what's missing, what's hard, and why. So first is bandwidth on demand really needed as a service? Many people say, let's just stay with IP, let's not do bandwidth on demand. So I'm not going to make a call here. I'm just going to give the for and against argument. And you guys can make a call on this one. So there is the against argument that bandwidth on demand is useful when there is shortage of bandwidth. That's why you need to reserve bandwidth. There is a lot of bandwidth in R&E networks. Best effort works well when there is a lot of bandwidth. And over-provisioning has traditionally been the way of solving these problems, and R&E networks are always provisioned and seem so for the foreseeable future, so why do we need bandwidth on demand? That's the against argument. The for argument is what we've been saying is that for certain large TCP flows, and this is a conjecture that needs to be proved, but for certain large TCP flows, even a small packet loss because of any interaction, and in this case 0.0046%, and all this work was done by Brian, who's sitting in the audience here, you can get only 5% of the optimal seed. What that means is that the data is transferred, but at 80 millisecond and 10 gigabits, I think this is where these assumptions are, 80 millisecond RTT with 10 gigabits per second, you only get data at few gigabits per second. I think this graph, next graph will show it more clearly. For 0.0046% loss and using TCP as your data transfer protocol, what we experienced, and this was measured, was that at around 80 millisecond here, you got, I think, around 5 gigabits per second? No, 5 megabits per second, right. 5 megabits per second. And yeah, this is around 10 gigabits per second, which is what it would be if there was no loss. So you see that if there is no guaranteed bandwidth, there is a huge impact to data transfer of large flows. So for mice flows, if you're browsing this, you won't see this effect. It doesn't matter. If you are very close by, that means you're doing it within the lab, you wouldn't see the impact of that. So that is the for argument for bandwidth on demand. So these are the two arguments, and for people like us who worry about large science data and making sure it's lossless and you get the maximal performance, we worry about these things, and that's why we worry about guaranteed bandwidth circuits. Now still on-demand piece is up for question, but at least we worry about guaranteed bandwidth circuits in this case. So the second discussion point on bandwidth on demand is that application drive the bandwidth on demand. Now what I would like to say here is that the bandwidth and throughput are two different entities. So bandwidth is a network property. It is 10 gigabits per second, 100 gigabits per second, 40 gigabits per second. But throughput is how the application experiences the network. So in this case, applications care about their throughput, but they really don't care about the bandwidth. So when you have a case where you want applications to drive bandwidth on demand or make a request for bandwidth on demand in the network, the question is it's hard for applications to decide that. And that has led to some of the adoption challenges on bandwidth on demand, because the connection between bandwidth and throughput changes based on many factors, including latency, loss, load, etc. So I'm going to give an example. For a telephone case, the user does not care what bandwidth they get. The bandwidth is fixed. They just pick up the phone, dial, it's established. So no user says, I want a 64 kilobits per second to talk to that. That's kind of pre-programmed by the application. But in a more RNE case, the way we have done it, we say application makes a service request to network provisioning software and requests bandwidth, and the question is, how do you automate the thing that you ask for certain bandwidth? How do you know within the application what bandwidth to ask? And that has been hard. Now it is also an opportunity for innovation, an opportunity for people to think about this. But to the first order of approximation, people have been saying, at least let me get the speed of the NIC. Or they come up with a local site policy saying this application needs 2 gigabits per second, and that's it. And it's good approximation for data movers. But are there other heuristics that we can apply? Can we identify the flows? Can we use perf sonar as a mechanism to see what available bandwidth is there and request that? I think there is a lot of opportunity for innovation where through heuristics, through data, you can figure this out and make it easier on the applications and the application developers. The third discussion point is that it is not an end-to-end operational service. And the reason is because it has been hard to get MPLS deployed at the end sites. So what this has been is from an edge of a WAN RNE network to the edge of another WAN RNE network. But the data transfer goes from end site to end site. So what happens is that number one, VLANs need to be configured manually at sites. So it kind of takes the oomph out of bandwidth on demand in a sense. And any contention in the local site network or any packet loss in the local site network actually causes the end-to-end performance not to be great. So then people question, why did I do this, right? So it kind of, even though it is a well-meaning, well-architected thing, because it is not end-to-end, because of technology, it does not work as well as people expect. And then it puts into question, is this really needed or not? Now, I think there is some hope here. And I think one of the things that we have been kind of helping get awareness and deployment of is Science DMZ. Now with science DMZs, and you move kind of the data movers right at the edge of the network with a capable switch, with data movers now that can move a large amount of data, I believe that the infrastructure, end-site infrastructure, will now support. So it may be an impetus for having bandwidth on demand actually take off. So that is something I'm waiting for and looking for. And there are a lot of universities in US that are deploying it. There are national labs that already have deployed it. So I'm very hopeful that this will kind of create this end-to-end path where the end-to-end path can be set up and be made clear, and it will lead to the adoption of BOD. So everything is not bad there, but it has been one of the reasons why bandwidth on demand has had some friction in getting adoption in the last few years. The other discussion point is it's not an operational service. And we have had this experience, especially, it has worked as a great production service within the network. SurfNet has it, ESNet has it, Internet2 has it, among others, a few other networks have it. It works great within the domain. But when it comes to multi-domain and something goes bad, we do not have the OAM procedures designed yet to debug that. So, for example, I think I'll quote some personal experience watching DINES and a project in US that is kind of trying to build a 40-node bandwidth on demand network around US. Eric Boyd knows that very well. But we've seen issues from certificate expiry to host switch, VLAN misconfiguration, simple operational stuff that happens across other networks, especially end-site networks, that you need to get 2 or 3 engineers aligned in order to figure out what really happened. Why didn't it work? And that is hard. So we need some OAM procedures on BOD, which has not been really worked on. And I think that is one of the things that has been kind of providing resistance to its adoption. And adoption. But what I conjecture is, in order to solve this, we require network engineers to participate with the software developers and the protocol developers to make it into a debuggable operational service. And we haven't had that interaction in the community yet. So I implore network engineers to kind of come work with the bandwidth on demand designers to know what kind of OAM is needed. I think I heard the last speaker talk about MPLS OAM. Yes, you need MPLS ping and MPLS trace route, and if you don't have that, it makes it hard to debug. Similarly, for this service, we need those kind of OAM tool sets that are not existing yet. And the last one on software and protocols or in continual evolution. So the focus of the RNE community has been to focus on consensus and standardization to increase adoption. So that's kind of what we focused on. We said, how do we get bandwidth on demand adopted? Let's standardize in an open environment, and let's build consensus. But one of the things we have noticed is that lots of software implementations. Now, if I compare this to SDN, and I say, if I take Open Daylight, there are a whole bunch of people contributing to one source. Now, not all of the modules of the source are well tested or well prepared, but they're all contributing to one source. We, for whatever reason, have 10+ implementations, and all of them research, develop, don't have the resources to do a lot of testing and make it full production ready, or it takes a lot of time. So that, to me, has been another one that has been kind of blocking the wide adoption, because we are not able to add all the debugging features and other ancillary features. We just have the basic functionality up and running. And again, the slow consensus building process in standards group with leave no RNE behind has led to delays in standardization. And because the demand side has varied, which means the applications don't know how to use it and they have not pushed for it, it has made it slow. And I think that is something that has been fixed. The NSI 2.0 protocol is done, so I feel fairly confident. But that has been part of what has been making bandwidth on demand slow to take off. So, one of the ways you can tell me is, you're being too hard on yourself in the, I've been wanting to see this. I've been working on this. So let's look at the commercial carriers. So in 2001, when I was working on this kind of stuff, there was no commercial carriers willing to do bandwidth on demand. But now they have it on their website. So Verizon has bandwidth on demand order guide, and it allows, again, it's SONET, of course, not MPLS yet, but they have a bandwidth on demand service. But it's a little bit different. It's, if you send the order before 1 p.m. Eastern time, we will have it working that day. So it's more a provisioning service rather than a dynamic application-driven service. And then AT&T has an optical mesh service, which is a bandwidth on demand service, which allows people to build circuits to different sites without needing multiple ports. I think that's where they save money. So carriers are building bandwidth on demand and offering it, so they are also moving along. We are still ahead of them, but they are also moving in this direction, but they are looking at it as a single domain still. So they are not tackling the multi-domain piece, which we are tackling. So I do want to say some caution. You know, we love our bandwidth on demand service because it has given us some value. It has saved a lot of engineering time for configuration, a lot of coordination time. We don't have to have a conference call and email chain with multiple networks in order to set up a circuit. It's fairly simple. But then there are long-lived circuits which have got backup and restoration. So this has worked well. Guaranteed bandwidth of scavenger has helped manage elephant traffic, especially the LHC traffic in our network. So I'm not saying it hasn't worked well. All I'm saying is it can be much better and it can be much more adopted, and there are certain friction points that have saved it, and I just want to bring that out and hope the community can work with that. So summary, I'm going to do a quick summary and path forward. So first thing I'm saying is let's rename bandwidth on demand, because part of it, what I've been listening to people and talking to people, is that it's not about bandwidth. It creates the wrong impression. It's more about creating networks on demand. It's creating virtual networks. Bandwidth is a property that you attach to it, and for some flows you can attach guaranteed bandwidth property to it, but it is about creating networks on demand, and I think that's something that all of you agree with. Let's focus on end-to-end. I think with SDN and programmability, we can take these MPLS circuits or SDN circuits or SDN flows all the way to the end. So let's work on that and make sure that happens. Let's collaborate with applications. So there is one experiment that Bill Johnson is running here with LHC1 community on a LHC 1.2 point experiment. So this is the first one. Now it is taking a fair amount of time because you're getting the standards right, but it is a case where the application community is engaged with using a network service. Let's figure that out. Let's make that an example of how this would work, and let's really figure out what is needed to break the friction point between applications. I really implore the network engineers to work with the BOD folks or the networks on demand folks to operationalize, because I think there is some set of tools that are missing that doesn't make them comfortable with it, because they cannot debug it, and because they're not comfortable with it, they won't champion it. So I think that is something that is missing. And I would still implore that collaborate with each other if possible. I know it is very hard to do that across time zones, across networks, across different funding models. But to me, fewer implementations of usable, supportable code is much more value than many implementations of research quality software. So I know it is a hard goal, but if we can get there, that would be great. Kind of that summary of my talk, and I didn't talk about SDN and programmability, but I'm going to have an epilogue. So let me have 2 slides on SDN and programmability. So one is, why call network on demand? And my conjecture is because of software-defined networking, there is more and more need for building overlay networks, network slicing, and network on demand. And when you build an overlay network, not all of these networks need guaranteed bandwidth. They just sometimes want isolation. I just want a VLAN with no guaranteed bandwidth. So, and also many science domains like LHC, K-based, biology, climate, they're all looking for multi-point to multi-point services, so not just point-to-point. So let's generalize from a point-to-point connection service to focus on building network overlays, call it network on demand, because I feel now the bandwidth on demand term is limiting because it kind of almost blocks people from talking about it or adopting it. So let's change the name and work with and build technology that works with over-provisioned network and best effort traffic, or works with guaranteed bandwidth flows. Depends on what your flow is and what you need, what the requirements is. It works with both of them. And software-defined networking, especially with network virtualization, will enable these network-on-demand concepts and constructs and virtualization constructs to form quite naturally. And the last thing is on SDN and multi-domain. I think the first speaker talked about that. And my conjecture is that multi-domain is hard. So no matter whether we change the technology on how we provision stuff, we still have to talk about security, authentication, authorization, debugging, operationalization between domains when you federate stuff. And those hard problems don't go away. So if we move towards SDN and multi-domain, I think we can learn from all the discussions in the community has been having around NSI and multi-domain and other things, because these problems that are being solved are the same problems that need to be solved whether it's SDN or not. And I think these are the policy issues and the layer 8 issues, and how do you do things, how does customers use, who's allowed to use what resource. These issues will not go away whether you change the technology from MPLS to SDN. So let's continue that topic and let's leverage that learning when it comes to multi-domain SDN. That's about it. Thank you.
Thank you very much for your presentation. Any comment?
I think that was a great talk, Inder. I guess to me the hard part, whether or not you have guaranteed bandwidth or not, I agree with your calling it networks on demand. Essentially, that that's what we're trying to do, and it's the interdomain aspect that we seem to constantly struggle with. I would point out one aspect that I didn't hear you talk about that I thought maybe was important, which comes from the CERN workshop over a year ago, is that in many respects, one of the challenges I think over the last decade has been that we've had network engineers talking to network engineers about how to design automated network engineering, and it really seems to have left the application community out. At the CERN workshop in particular, the comment that struck me the most, I think it came from the ALICE project, was basically, I don't really care about any of this. The only thing I need to know is whether or not to kill the job or not, and to do that I need predictability. It doesn't matter how fast or slow it is, it just needs to be predictable enough that I know when to give up on the job and start on a new job, because I'm doing 1 million jobs a day or whatever it is. Yeah. And that part of the conversation I had never really heard coming from the network engineers talking to each other. So I would say that if we're going to try to refactor this and think it through how to approach it, having an application-driven approach as opposed to a network engineering approach would probably be very, very helpful.
Thank you. Good comment. I'm hoping the LHC1 experiment will help us get there, and then it'll be an example for other applications and make it simpler to adopt other applications. But again, that is still started. It's in progress. Let's see how that goes. Thanks.
Hi, Rob Evans from JAT, and just wanted to echo Eric's comments there. That was a great talk, Inder. And to further echo Eric's comments, right, bandwidth on demand is a name that's been holding us back, and it needs to go. You mentioned the carriers. In the UK, there's a company called Lego Networks that is offering this bandwidth on demand, literal bandwidth on demand, as an operational service now. But again, that's single domain. You're right, it's the multi-domain aspects that we need to start thinking of, the security, the authorization, the debugging, and that's where we can really help our users.
Thanks for your comments.
Yeah. Yes, I have only one comment about if we think about not bandwidth on demand but network more on demand. It exists right now, a very popular protocols that is deployed between each other, between older and RAN, which is mainly MPLS. MPLS interdomain works fine. So we can create very easily on demand a network between different domains. It exists, it works, it's fine. It doesn't provide any guarantee right now, but we can work on this very easily. At least we have the connection that works right now. And
this is the VRF solution? Are you talking about the VRF or?
No, the point-to-point of VPLS.
Okay, VPLS. How does VPLS work between domains right now?
Thanks to a BGP label unicast peering between the domain. Okay. And we make it work in Europe right now.
Okay.
So we are ready to make tests with you, if you want.
Thank you. I was not aware of that, so I'll, yeah.
Okay. Last but one there. And
yeah. Thank you, Xavier, for your comment. I just wanted to join the voice of Inder and say that, the bandwidth thing is really hard to deliver, both at the ends. So at the endpoints, we tried that for the last year, and we always got hit in the Xiang community. And secondly, I think in the core networks, it's also really, really hard to deliver bandwidth guarantee. That's also what we experience, because most networks are not built to do that today. So you're absolutely right. We need to move on and do something else. So it's more about the network on demand rather than the bandwidth on demand, I would say.
So I'm not throwing bandwidth on demand away. I'm saying bandwidth is a property, and you have to apply it to certain flows that need that guarantees, but you need more than that.
Yes. But what I'm saying is that you're going to have a hard time. You're doing that on demand, bandwidth on demand in all the networks, for instance, in the Xiang area. That's, I wouldn't say impossible, but
And I noticed that different networks have different capabilities, and not all networks will have that capability to provide that. So we need to be able to work with that.
Yeah. Thank you.
Last comment.
Hi, Inder. Thank you for the talk. I really enjoyed that your sort of retrospective view and looking at things like a phone call being a dedicated circuit. So my question is, in your experience, having seen many of these attempts at doing this, would it make sense to maybe split the building of overlay networks with the guaranteed bandwidth, so that you leave the overlay network building to the end site, and maybe in that way solve the inter-domain problem and the end-to-end problem? Because we know that something like IP already works into domain and already works end-to-end.
So I can think of them differently, but how do we solve the guaranteed bandwidth problem for flows that need it? So that, does it still need to get solved by the current way, and IP becomes a multi-point to multi-point? Well, IP is a multi-point to multi-point, but then you have isolation. And I think that's where it becomes a problem, because when you go multi-domain right now, you go best effort and you don't have that isolation. You lose the VLAN tag or whatever be your VPN tunnel. So I think that building a network overlay multi-domain, you require the building block of building a circuit multi-domain. So that becomes your building block. You can add a bandwidth as a property if the network support it, or if not, then you don't add it as a property, because that's not a capability that is supported. So you kind of make, so you take the bandwidth on demand as a special case of a multi-point to multi-point network. So you make that a special case rather than that being the only case that we focus on. That's kind of how my approach is. I don't think we can get rid of it completely.
Okay, last quick.
Short remarks. So it was a great talk, Inder. I really enjoyed it. Also, I've been working now for about 17 years in this, since ATM, and going through the different cycles. So I noticed that you come up again with, well, we need to solve the AAA problem, and we need to solve this, and we need to solve that. And then I'm thinking, oh yeah, but shit, we did publish that already, or another group did publish that already. So it seems that the younger generation, if I'm feeling that old, so the younger generation is starting to redo several of the problems which are invariantly, so computer science-wise, already published. So it would be good if we, as this community with its special needs for cyber infrastructure, somewhere have a place where we put that information which was already sought out, articles, and the principles, the invariant principles, that we put them somewhere. For example, I'm currently reading 2 theses, and they will come out in the next few months about creating virtual internets and overlays, and one on multi-domain authorization by our beloved friend Leon Gommans. So, but there's more work. I cite from my group, but there's way more work in the community. So if we can get that information somewhere, then we do not need to redo and repeat history all the time.
Okay,
that is true. Case, I will look for brainstorm ideas how to do that. It's been hard, I understand. We did this in 2004 in a SC demo, so it is what it is.
Okay, thank you very much for inspiring talk again. Before you leave to have a coffee, two quick announcement. One, don't forget your badges for the gala dinner. And the second, if you need some assistance to traveling to the airport tomorrow, you can ask some help at the registration desk. Thank you very much, and have a nice coffee break.